Hi and welcome everyone. So in this video, I want to go over the inverse of a matrix. Now let's go over the definition first. First of all, if you want to find the inverse of a matrix, that matrix has to be a square matrix or an n by n matrix. So we say if there exists, again, this symbol means there exists a matrix B such that A times B is going to give us In and B times A is going to give us In, and let's go over In. If you haven't seen this before, I'm sure you have. In is the identity matrix. So In is just the matrix that has ones in the diagonal and zeros everywhere else. So, and if you take a matrix and multiply it by the identity matrix, you're going to get the answer will be always that matrix. And I put an example here. I2 is 1, 0, 0, 1, and I3 same way. You're going to have 3 ones in the diagonal, zeros anywhere else. So coming back to that, if we have those, AB is equal to In and BA equals to In, then A is said to be invertible or non-singular. So remember, non-singular means invertible. B is the inverse of A, and B is denoted as A to the power of -1. Whenever you see this, that means the inverse of A. And always we know that A times A inverse is the identity matrix. So each time you have a matrix and you multiply that by another matrix and you get the identity matrix, that means those two matrices are inverse of each other. If A is not invertible, that means we can have an n by n matrix and that matrix will not be invertible. Then it doesn't exist a matrix B such that we have all these conditions. So, and if that happens, then A is said to be, and if you see this ISTB means it's said to be non-invertible or singular. So a non-invertible matrix is also called a singular matrix. Now, the first theorem that you need to know, if A is invertible, then its inverse is unique. That's called the uniqueness theorem. Let's go over the proof of that. Let's say A is invertible and it has two inverses, and B and C are the inverses, both are inverses of A. So we know that if A times B is going to give us In and B times A is In, A times C is In, and C times A is also In, because A and C are the inverses of A. Now we can start with number 1. We can write this down, multiply both sides by C on the left. So you can say CAB times CIN, but CA, we know that is also In. So you say In equals to C times In. So again, instead of CA, you can put In. But what is In times B? A matrix times the identity matrix. The answer is always the matrix itself. And C times In is said, therefore B equals to C. So inverse of an invertible matrix is unique. That's the proof. And learn this also if you haven't seen before. Whenever you finish a proof, you can just put QED. That means quod erat demonstrandum in Latin, is what needed to be demonstrated or proven. So sometimes you might see this in the books or in the mathematics articles. Let's go over the properties of inverse matrices. First, let's say A is an invertible matrix. K is a positive integer, and we can say C is a non-zero real number or scalar. The first property, the inverse of an inverse, is just the matrix itself. So the second one, a to the power of K, inverse is the same thing as A inverse to the power of K. So these two are equal. Just be patient, the proof is coming. The inverse of CA is the same thing as 1 over C times the inverse. Then the inverse of a transpose is the same thing as the inverse transpose. So, and number 5, AB, the product of the inverse is the same as B inverse times A inverse, and we call that the inverse of product. So before going over the proof of those properties, let's see how we can find the inverse of the matrix. 2 by 2 is pretty straightforward. There's a technique to find the inverse of a 2 by 2 matrix. Let's see, if you have A is A, B, C, D, then the inverse is 1 over AD minus CD times, you switch the places of AD, so you put DA and the signs of C and B. Let's do an example. So if A is 1, 2, 3, 4, if we want to find the inverse, then we write 1 over 1 times 4 minus 2 times 3, and that's -1/2. You switch 4 and 1 and you change the signs here. So it's 1 over -2, 4, -2, -3, 1. And if you multiply the -1/2, you get -2, 1, and that's 3 over 2 and -1/2. So that's the inverse. If you want to check your answer, you can take the matrix and multiply it by its inverse, and you should get the identity matrix. And I can do, let's just do this first entry to multiply, get that. Again, you take that row and that column, and I did it here. 1 times -2 plus 2 times 3 over 2 is going to give you -2 plus 3, which is going to give you 1. You want to get this one, let's just try it. So it's the first row and the second column. 1 times 1 is 1. 2 times -1/2 is -1. So you get 0. Finally, if you do that, times that, 3 times -2 is -6. 4 times 3 over 2, it's going to give you +6. So it's 0. And if you want to find that entry, 3 times 1 is 3. Minus, because there's a negative, so 4 times 1/2 is 2, and that's going to give you 1. So that's how you can find. If you have a 3 by 3 matrix, so the way, or 4 by 4, that's one way of finding the inverse. So you write your matrix, and you can write the line and write the identity matrix on the right side. So then you do the row operations or row reductions until you get the identity on the left side, and then whatever is left, the matrix that's left on the right side, is the inverse. So for example, for this one, this is our A, and that's the identity. So what you want to do is make this the identity. So you can do -1 R1 plus R2, and that's going to change R2, and 6 R1 plus R3, that's going to change R3. So you want to basically make these two 0, and you do that for all of them, every single entries. So like when you do that, then you want to, of course, you want to make this 0, so you can say 4R2 plus R3, and then that's going to change R3, and if you do that, that becomes 0, and again you do for every single entry. And as you know this, you notice the entries are changing here, and you can add -1 times R3. So if you do that, I kind of this fast, but then that's what you get. It's just simple, the 3 row operations you perform until you get the identity matrix. And you just keep doing it, and once you finish all the operations, you see the identity matrix here. So this is the inverse of our original matrix. And if you want to see if that's right, if you take that matrix and multiply it by 8, then you should get the identity matrix. So you can find the inverse of a matrix by row reduction. Now let's go over the proof of some theorems. So some theorems, if you want to prove it, what you can do is multiply both sides by the inverse, and then if you get the identity matrix, that means those are equal. So the left side we have that, and the right side we have this one. So if we multiply the inverse of CA is just CA. If we multiply CA inverse times CA, we know that automatically is going to give us I. Now let's see what happens if we multiply this side by CA. If we multiply the right side by CA, we can write this as 1 over C times C, and A times A inverse is already, this is I, this is 1, so you get I. So when you multiply the left side by C8 and the right side by CA, you get I. So that means the left side equals to the right side. As we said, the inverse of matrix is unique, so they have to be equal to each other. Next, AB is invertible. So given that A and B are invertible and n by n matrix is proof, we want to prove this theorem right now. So we're going to do the same thing. The left side, we have that, and the right side is that. So we take the left side and multiply the inverse of AB is just, or AB inverse is just AB. If you multiply AB inverse times AB, we know we're going to get the identity matrix. Now let's try the right side. The right side is B inverse times A inverse. So if you multiply that by AB, what happens is we can separate them. So you can say B inverse, and in the middle we can just write A times A inverse times B, but we know that A times A inverse is I, and we can take that I n out. We're left with B inverse times B, and that's also I n. Now multiplying both sides by AB, we get I n. So let's write the conclusion. AB inverse is the inverse of AB, and B inverse A inverse is also the inverse of AB. We proved that. So the inverse of AB is unique, and that's from the uniqueness theorem. Therefore, we can say AB inverse equals to B inverse times A inverse. That you want to put QED here, you're more than welcome to do that. Next one, if A and B are two invertible n by n matrices, then their product AB is also invertible. Let's go over the proof of that. We know that the identity matrix can be written as A times A inverse, and that's A times IN times A inverse. But how can we write IN is B times B inverse? So then we can separate them. So if we separate them, then we know that AB times B inverse times A inverse from the previous theorem, then we know that's going to give us IN. So therefore, we know that AB is invertible. Or you can substitute here. Instead of B inverse times A inverse, you can just say that's AB inverse, and that's from here, and you get IN. So therefore, it shows that AB is invertible. So AB is invertible, and the inverse is B inverse times A inverse, or we can just say it's AB inverse. Now let's go over this one. We're going to try to prove this one. A to the k power inverse is A inverse to the k power. So first, we know that's invertible. The right side, if we multiply A to the k power by A inverse to the k power, so I just took that one. Okay, first of all, let's see how we can write the right side. That's what we're going to do. So A to the k power is A times k times, and A inverse to the k power is A inverse times A inverse times A inverse. Then we can just take one by one. So if we do that, then we get IN. So what's left, we have k minus 1 times and k1 minus 9 times. And if you keep doing this, then you're going to finally end up with IN. So if we take the left side, which is AK, and multiply by AK inverse. So if we take this left side and multiply it by AK inverse, we know we're going to get IN. So multiplying both sides by AK, so we took the right side and multiplied it by AK and we got IN. And the left side is pretty straightforward. If we take that and multiply it by AK, we do get IN. Therefore, both sides are equal again by the uniqueness theorem. And we know what the uniqueness theorem is. What by now? Very important, if A is a square matrix, if its row equivalent to IN, what's the meaning of that? That means if you take a matrix and do the row operations and you get the identity matrix, then IN is invertible. So if you take a matrix and do the row operations and you don't get the identity matrix, then that matrix is singular or non-invertible. Also, if you have an n by n matrix and that matrix is invertible, then the system AX equals to B, or you want to put vector notation, has a unique solution. Let's see how we can find the solution of that system. AX equals to B, you can multiply both sides by A inverse. And you know that A inverse times A is going to give you the identity matrix. And that's going to, this side you have A inverse times B. So X is A inverse times B. You can get the answer. Let's do a simple example so you understand that. If you have this system, you can solve this system by any method you want. If you do that, the solution is 13/5 for X and -2/5 for Y. Matrix notation, so you can, the matrix of the coefficients are, that's 1 and that's 1. So you have this times xy equals to B, which is 4, 3. A times X equals to B. So what we need is the inverse of this matrix. And that's a 2 by 2 matrix. You can easily find the inverse. So it's again 1 over that times that minus that times that, and or change the place of A and B and put negative signs for that. So please check the formula again. If you do that, that's the inverse. You can find the inverse. Now, if you take the inverse and multiply it by the constant column, again, matrix multiplication, that times that plus that times that is going to give you 13/5. 1/5 times 4 minus 2/5 times 2 is going to give you -2/5. Conclusion, again, this is X and that's Y, which is the same answer. I think that's it for this video. I'll see you on my next video. Have a good one. And thank you for watching.